Yeah, thanks a lot, Professor Deng, for the nice introduction. I'm Pinye Lu from Shanghai University and Finance and Economics. Today, I will talk about optimal marketing design, and I will talk about that from two perspectives, simplicity and robustness. Actually, this is a very simple question. This is called Bayesian revenue maximization. So a seller is selling some item to a number of agents, and the seller don't know the valuation of the agents, but he knows the distribution of the valuation, and the seller would like to maximize his expected total payment. That's a simple question. And here we focus on the very simple case, the first for the single item case. So that seller only sells single item to a number of agents, and he don't know the value, but knows the value distribution, and he wants to maximize his expected total payment. And I think you all have the experience to buy something. So if you buy something from the market, offline or online, the most simple way to sell an item is just set a price. The seller set a price for the item. Then, as a buyer, you will buy the item if you value the item more than the price. So basically, if he values the item more than price, he will take the item, pay plus P, and otherwise he will leave the market and pay zero. So as a seller, you want to set a price, maximize expected revenue. If you set the price too high, then if you the item is sold, then you got a big revenue, but the probability of selling is become low because maybe no one would like to buy the item. But if you set the price low, then the selling probability is high, but the revenue is also low. So it's a kind of trade-off between the price, the revenue, and the selling probability. So this is actually a very simple optimization problem. Let's take one. Let's do the math. So the revenue is the expected revenue is equal to the price times the selling probability. The selling probability is that its formula. So the selling probability is equal to the probability that at least one buyer values the item higher than the price P. So this is 1 minus the probability all the agents value the item less than P. So we assume that the valuation for different agents are independent. So this is a formula. So we want to choose a P, maximize this quantity. So take a very simple example. If you only have two buyers and the value distribution is uniform from 0 and 1, then this probability is just P, and the revenue formula is like that. So we can do calculus, and we know that this quantity achieves the maximal when P is square root of 3 over 3, and the maximal revenue is 0.3849. So that's a very simple. But so if you want to set price, this is the best price to set. But is this the best way to sell the item? Actually, it's not. The seller is able to increase the revenue by doing something smart. So one thing is he can do the sequential post-pricing. Namely, he can post different price for different seller. That's actually quite common, especially in the online business. If you search the air tickets in website, you will see different price for different person and a different time. So basically, the seller can sequentially post a different price PI to the ICE coming buyer. Then the item is sold to the ICE buyer who first values the item larger than his particular price. So the price is different for different buyers. So in this way, it's possible for the seller to extract more revenue from the buyer. So this is a formula for the revenue for sequential post-pricing. So it's summing over all possible buyers and the price PI, and here's the probability that the item is sold to the ICE buyer. So first, the condition is that this ICE buyer should value the item larger than his price PI, and another probability is that he has a chance to buy the item, meaning that all the buyers before this particular ICE buyer values the item less than their price, so that this ICE buyer has a chance to buy the item. And to get optimal revenue, it's very natural to set the price in decreasing order. So you set price higher first to try, and if you get rejected, you set a low price. So that is optimal. I mean, it's easy to see that there's no point to do otherwise. So let's back to the example. So for this sequential post-pricing, the idea is that if some buyer values the item higher, then you should set up higher price for him. But actually, even in the case that the buyers are identical, it's still beneficial to set different price because they come in order. So let's back to the example. There are two IID buyers with value uniform from 0 to 1. Then it's easy to write down the formula. It's the P1 and P2 are the two price set for the first buyer and the second buyer. So it's easy to maximize this formula and to get that if P1 is 5/8 and P2 is half, this formula reaches maximum, which is this number, it's 0.3906. Let's recall that this is the maximal revenue you can get for uniform pricing. This is indeed higher than that, even for the identical buyer. So this is, you can see that there's some smart way to extract more revenue. But pricing is not the only way to sell items. Another way to selling item is auction, to organize auction. So I think people are all familiar with English auction. So in English auction, people are in the same room and the buyers alternatively increase their bids. Until some points, only one buyer remains. Then this particular buyer is the winner. He will get the item and pay his last bid. So this is auction. So in this, if you organize an auction, it's conceivable that you can get more revenue in some cases. So, but to organize this kind of auction in a same room is quite costly. So you need to organize. You could bring together every potential buyers in the same room, which is only possible for very valuable item. For like a cheap item, this is not really feasible because the additional overhead is too high. But it's actually there's another format of auction which can solve the problem, which is called shared-based auction. So in this way, you don't need to bring everyone in the same room. Actually, everyone submits their bid, which is indicates their valuation of the item separately and but privately to the auctioneer. So it's very natural that the agent who bids the maximal, the highest value will win the item. But the tricky part is that how much should he pay? So if the one natural idea is that just pay what he bid. So if that's the case, let's think from this this B1's perspective. He bid $150 and got the item, and he will pay that. But he will think about that. If we decrease his bid to like 140, he still wins the item but pay a low price. He can actually further reduce to like 130 or 121, something like that, and he still gets the item and pays low and low. So actually, it's an incentive for the agent to lie to kind of bid a low price. But without knowing the value for others, it's it's quite difficult and confusing for the agent to bid what to bid. So to solve that problem, we actually have a very nice idea to so-called second price auction, which actually we wins the Nobel Prize for this, mainly for this contribution. So the idea is that still the highest bid win, but it don't pay his own price, her own bid, but pay the second highest bid. In this case, B1 wins, but he pays 120, which is the second highest bid. So in this way, it's easy to argue that this auction have a very nice property. It's called individual rational in the sense that everyone telling truth will have a non-negative utility in the auction, and another is called truthfulness. Truthfulness in the sense that to bid his own value is actually the dominant strategy. let's took the example. So in this case, if the first guy misreport his value to a high value, it's actually not don't change the output. If we misreport to a low value but higher than 120, then now changes the game. But if we report some value is lower than 120, then he will lose the computation, and actually it's worse off. So it's very easy to argue that for every agent, and no matter what other agent base, it's the best strategy for him to just telling the truth. And actually, this is if you think about that, it's not difficult to figure out that this is actually equivalent to the English auction, but not need to hold in a same room. Basically, everyone will alternatively increase their bid next from 0 and to the point that the bid reaches 120, maybe 121, and no one will follow except the first one. So the first bid will pay roughly 120 and win the game. So this second prize auction is in a way equivalent to the English auction, but this can be done distributedly and not simultaneously. That's a good part of second prize. So back to the example for the two IIG buyers with uniform value 0.1. If you calculate the revenue from the second prize auction, it's like 1/3, which is actually even low. But in some cases, the revenue here is actually high. So this actually raises a question of optimal auction design. Auction is actually an economics term, and the pricing can be viewed as a special auction mechanism. It's actually a very simple and special auction. They are also chooseful because it's a very simple take it or leave it mechanism. And we also focus on chooseful auctions, and we want to ask the question, which auction mechanism maximize expected revenue for the seller? And this problem is already well answered by Myson, who also wins the Nobel Prize. This is actually Myson characterized the optimal auction in the single parameter design environment. So basically, at the core of Myson's theorem, there's a lemma called the Myson lemma, which saying that to make the auction chooseful, the allocation rule must be monotone, and the price is determined by the allocation in a way. And then by that lemma, the total expected revenue is equal to this quantity, and in this quantity, this fee is called the virtual value. And from that, it's very easy to see that you just choose the bid with the highest virtual value and highest non-negative virtual value, because this virtual value could be negative. So if the distribution is regular in the sense that this field function is monotone, then the optimal auction is to allocate the item to the bid with the highest positive virtual value. So basically, it says that it's not necessary to allocate the item to the highest bid, because different agents have different distribution. It's kind of discriminate the different person. If you value the item high, it's possible by this Myson's auction to charge the person higher price. So in the special case of all the bids are identical, then this virtual value function becomes the same function because all the distribution are same. Then and in particular case for the regular distribution, then highest virtual value is equal to the highest value. So in that case, this becomes the second price auction, but not exactly, because we still need the virtual value to be non-negative. So we need the value to be higher than the inverse of the 0 for the virtual value function. This value is viewed as the reserve price. So basically, it's almost like the second price auction, but have a reserve. So this is also equivalent to the English auction, but with a starting price. So in a typical English auction, we are not raising the the price starting from zero, from some prefixed value, then this is exactly the second price auction with reserve. So this reserve is the starting price in the English auction. Okay. So I would like to mention that for non-IID valuation, this second price with reserve is not necessarily the optimal. As I said, the optimal one should be to give the item to the highest virtual value agent, not the highest value. Okay, but this is still widely used even in the non-IID valuation because it's fairness, and because the Myson auction is not fair in the sense that he will discriminate agents with different distribution. So back to the example. So it's very easy to calculate that for this particular case, the optimal mechanism is the second price with the reserve 1/2, and then you can calculate the revenue, which is this number, and let's do the comparison. So this is a price for the this is revenue for the uniform pricing, and this is the optimal revenue for the sequential post-pricing, and this is for the second price. So you can see that indeed this optimal revenue is indeed the highest. But we care how large could that gap be. So you may wonder why we care about this, since we already know the optimal auction. There's other constraints about the mechanism. Usually simple is better. Like say two perspectives. One is that the simple auction, like the anonymous pricing, it's fair. It's not distinguish different agents, which is very good property. Other thing is that pricing, like pricing scheme compared to the more complicated auction scheme, is more it's better in the sense that there's no need of much communication between the auctioneer and the buyer. Since the seller just set a price and there's no communication needed, and it's more privacy because in the auction scheme, the buyer need to submit their valuation to the auctioneer, and they may leak some private information. So it's conceivable that if the revenue gap between a simple mechanism is not too large with the optimal one, sometimes in some scenario, people may prefer the simple one, even if it's not optimal, because they have other advantage. So in this work, it's very interesting to characterize for different auction schemes how large the maximum possible revenue gaps between different auction. So we mentioned the four mechanisms, which is also for most widely studied and used mechanism in the literature: the anonymous pricing, sequential post-pricing, the second price auction with anonymous reserve, and the Myson auction. So these two are pricing scheme, and these two are auction scheme. These two are fair in the sense that they do not do prime discrimination, and these two have prime discrimination. So they are in this order, and we will study the revenue gap between any two of them. So this is the joint work with Jin Yaonan, Tang Zihao, Xiao Tao, and the stock paper is also joined with Qi Qi. So our first gap is between the anonymous reserve and the anonymous pricing. So this is studies the relative power of auction versus pricing when no discrimination is allowed. So both mechanisms are fair, but one is auction, one is pricing. So what is the power of auction in this sense? So we get a tight ratio of pi square over 6, which is equal to 1.64, which is not too large. This tight ratio means that for any possible instance in the sense of the distribution and the number of agents and everything. So for all possible instances, the revenue gap is less than this number, and there exists certain instance that the gap is equal to this one. So this is a tight ratio. And we will give very brief proof sketch because among all the gaps, this is the simplest one. So it's I can give a very brief outline of the proof. So for this two mechanism, actually like anonymous pricing and second private anonymous pricing, the only for instance, the only important thing is that the distribution of the highest bid. In the anonymous pricing, if the highest bid is larger than P, you will selling item. Otherwise, you are not. So this is the only important fact value for the anonymous reserve. So you can actually write down the CDF of D1 as this quantity. Also for the anonymous reserve, the second price with anonymous reserve, the only two quantity where change the mechanism is the highest bid and the second highest bid. So we also write down the CDF for the second highest bid, which can be written in this way, and it's actually have the term of D1 here, and also something about other distributions. So with that, we can actually write down the revenue for anonymous reserve and also anonymous pricing. So anonymous reserve is in this formula, and anonymous pricing is very, very simple, as already written in a previous slides. It's the price times the probability that the probability of selling, which is 1 minus the probability of the CDF of X for the highest bid. So with this formula, actually, we can write down the revenue gap is as a mathematical programming in this way. So we want looking for all the possible instances with the anonymous reserve price is less than 1. So how large is the anonymous anonymous pricing revenue is less than or equal to 1? How large the revenue from the anonymous reserve could be. So this the optimal value for this mathematical programming is exactly the worst case revenue gap. So we basically manually solve this mathematical programming, and this is actually very simple because there's only actually two variables, and we do some bounds based on the constraints, and we see that this D1 is larger than this quantity, and D2 can relate with a bound to D1. Then finally we can get the calculation. I will not go to detail, but you see that with the constraint, so the maximal value for that is equal to pi squared over 6, which gives the tight bound. Of course, this is an upper bound part. We also need to provide an example showing that this bound is indeed achievable. Okay, this concludes the proof of that, which is the simplest among all other gaps. So we also studied the gap here. So these two are both pricing scheme. So we are studying the pricing scheme, but sequential post price allows the discrimination, and anonymous pricing don't allow. So this is also very interesting comparison in pricing scheme. What's the power of discrimination? And we also get a tight bound of 2.62, which is a bit larger than the previous gap here. So as I said, the meaning of tight ratio means that it's optimal. So this proof is much more complicated, and I can only give a very high level idea. First of all, we also use the mathematical programming to capture the tight gap as before. And one very important observation is that in the worst case, each agent is of triangular distribution. So triangular distribution meaning that their distribution it's not CDF, but the quantile revenue curve is of a triangle. So basically in that formulation, the regular constraint means that this curve should be concave, and triangle is kind of in the boundary of this concave family. And we observe that to compare these two mechanisms, the worst case means that the largest possible gap appears when all the agents is of triangle distribution. And for triangle distribution, we can actually captures the distribution by two quantity. So it simplifies that a lot. And it's also interesting to observe that in the worst case, the Bayesian probability for each agent is infinitely small, and there are infinitely many bias. So the worst case actually have larger number of bias, not like some other cases like 2 bias or something like that. And the proof is very, very complicated. So we also studied the gap between Bayesian auction and anonymous pricing. So this is a comparison between the optimal one and the simplest one. And we actually get the same tight ratios, 2.32. So with the same gap here. And this proof is even more complicated because it's not true that the worst case happens for triangular distribution. So we actually need to carry on all the parameter in the proof, and it's very complicated. Also for this gap for the Bayesian auction and anonymous result. So this is these two are both auction scheme, and this gap studies the power of discrimination in auction. Like this gap studies the power of discrimination in pricing scheme. So for this one, when the problem was first asked, they get a low bound and up bound for the gap 2 and 4, meaning that they proved the gap is at least 4, and they give example showing that the gap is at least 2. And then this bound, the up bound was improved to E, like 2.7 something. And both of their paper actually conjecture that this low bound 2 is tight. And in our paper, we disproved that this conjecture, showing that this low bound 2 is not tight, because we improve the low bound to 2.15, meaning that we actually construct an example showing that the gap is at least this number, and we also improve the upper bound to here. But here they are not same, meaning that it's not tight, so they are still a gap. So what is the optimal gap between these two auction scheme is unknown, and I think it's a very, very interesting open question. And also the gap here is also open. There's an upper and low bound, but it's not closed yet. So these are open questions. So now let's move on to a more realistic case. So previously we are selling one single item. So now we move to the multi-unit setting, means that the seller have k copies of the same item. So it's the same item, but there are multiple copies. And the buyers are unit demand, in the sense the buyers are only interested in get one copy of the item, not necessarily get more. And I think this setting is more common than a single item in real business, because usually the company or seller have produced multiple copies of the same item and just want to sell that. And in this setting, since although it's a multiple unit, but it's the same item, and the buyers are unit demand, then the Bayesian auction is also optimal. I will not go to details. As you need to. It's not because there are k copies, not like a single item. You actually choose k case the k highest bit, k highest bit with highest virtual value and which is non-negative. That mechanism is called the Bayesian auction. In that sense, is also optimal. So we also study the relation of 4 different mechanism in the multi-unit setting. Here, everything else is the same, because the anonymous pricing can be naturally extended to multi-unit setting. Sequential post-pricing also naturally extend. Bayesian is still optimal, but here is not second price auction with anonymous. It's k+1's price auction, because we have k items, we can sell that to k different persons, so it's not second price. So everything else is similar. So with Jing, Jiang, and Zhang, we studied the relation between any two of them, and the conclusion is that So these two gap. So for the gap here, they are both fair mechanism in the sense that they don't discriminate different person, but one is auction, one is pricing. Here, both of them discriminate different agents, but one is auction and one is pricing. So these two gap measures the power of auction in the non-discrimination setting and discrimination setting. And we prove that both gap is 1 plus theta 1 over square root of k, which means that if k is very large, this is a very approach 1, meaning that the gap, the revenue gap vanishes when k is very large. So basically, the power of auction is very small, and if k is large, it's actually better off just do the pricing because you don't need the communication and also the privacy concern. So the power of auction become very small when k is large. This is also what we observe from real life, because if a company produce large number of copy of the same item, it's not usually not a good idea to do it by auction. Selling by pricing is good enough. Also, we calculated the gap here. The gap here is actually because we already know that for large K, these two auctions is almost the same, and these are all the same. So this is a gap between two groups. And the distinction is that this group allows prime discrimination, and this group disallows price discrimination. And we show that this gap between the two groups is in the order of log k, which is actually very large. If k is large, meaning that it's really beneficial to do price discrimination if there are many copies of the same item. And this is also what you observe in real business, and the price discrimination is very common, and because this is very beneficial. Okay, so if we move further to multi-item setting, multi-item here previously is multi-unit. It's actually same item but multiple copy. But for multi-unit, it's become much more complicated. I will not give much result, but just showing some example. By doing that, I will give you a sense that for multi-item setting, it's quite complicated. So let's take this example 1. So we have 2 items with ID distribution and take values from 1 and 2 as 2 discrete value with equal probability of half. So in this case, the buyer, actually a single buyer, is additive, meaning that if we get 2 items, the value of the package is the sum of the value for each item. So in this case, if you sell the 2 items separately, because it seems that there are no relation between 2 items because they are independent and it's additive, there's no point to sell them together. If you sell them separately, the total expected revenue is 2, because if you set the price to be 1, it's the selling price is 1 and it's 1. So for 1 item and 2 items 2, if you set the price to be 2, the selling probability is half, and the expected revenue is also 1. 2 times 0.5 is 1. So if you sell the item separately, the total expected revenue is 2. But actually, there's a better way to do the selling. If you bundle the item together and set the price 3. So you're saying that I'm not saying the item separately. You either take both item or leave it, but the total price is 3. In that case, there's 4 possibilities. So the values, the buyer's valuation for the first item could be 1, 2 with equal probability. The second item is also 1, 2. So except the case, the valuation is 1, 1, which total value is 2, which below 3. So the buyer will not take the item. For all the remaining 3 cases, the buyer will take the item and pay 3. So this is the selling probability. It's 3 quarter, and the expected revenue is 2.25, which is larger than the revenue for selling separately. So from that, you can see if there's multiple item, it's not necessarily graded separately, even in the additive case and independent case. And my second example showing that selling as a bond is not necessarily a good strategy, because if the value is 0.1, not 1.2, you can see that selling separately have a better revenue. So it's not necessarily one is better than other. It depends on the valuation. So in some cases, selling separately is better, and in some cases, selling bond is a good strategy. But that's not the end of the story. Let's see the example 3. So here, the two items have 3 possible values: 0, 1, 2, with equal probability. So in this case, if you do the bond selling or selling separately, as you can calculate, the revenue is the same. It's 4/3. So that's the revenue you can get if you do either as a bond. But actually, there's a better way to sell the item. So how to do that? So basically, the idea is that you set a price 2 for each item and a discount price for the bond. Discount price of 3. So basically, this is in Chinese called 第二届半价. So if you get 1 item, you pay 2, and if you get 2 items, you can pay a margin of 1 for the second item. So in this way, you can do the calculation. So with a certain probability, which is 2/9, which namely the value profile 0, 1 and 0, 2 and 2, 0. In that case, the buyer would only like to take 1, even for the discount price, not willing to take the second one, because for the second one, his valuation is 0. So in that 2 case, you will sell 1 item at price 2, and the revenue from here is 4/9. And for the probability of 3/9, which is like 1, 2, 2, 1, and 2, 2, these 3 cases, the buyer will get the item with price 3, and the revenue is 1. 3 times 3/9 is 1, and the total revenue is this one. This one 13/9, which is larger than the revenue we can get for either selling separately or selling a bundle. So this is a very, very tricky way of set the price. Is actually the best one. Even more complicated in the example 4, we can get that the optimal revenue will do some lottery. So basically, you pay some price, the outcome of that is not determined. You will flip some coin, like with probably half, you get something. It's quite complicated. I'm not going into that detail. So all the message here is that for multi-item auction, there's no good capitalization even for the optimal mechanism. So there's no something like called Mason auction for multiple item. And computer scientists got some computation results saying that if you are given all the parameters, you can compute the optimal mechanism, but it's not quite complicated. So they also studied the simple versus optimal question there, got some solution and made some progress and more open question. So that's the message. Okay, now let's move to the second theme of the talk. So first part is about the simplicity, about the simple versus optimal, and the second part is about the robustness. So from the previous discussion, we can see that all 4 mechanisms, which is widely used, accuracy depends on the value distribution. Even for the very simple anonymous pricing, you need to set the optimal price based on the distribution information. Without knowing the distribution, you cannot set a good price, or you cannot design a good auction. So, but in real life, the seller will not have a complete value distribution information of the buyers. So can we do that? Can we still kind of design a good mechanism with very little distribution information, or there are many uncertainty? So So this is called the robustness. So basically, we have some hidden information or we have some uncertainty in the information, in particular in the information distribution. Can we do that? So for the uncertainty in the distribution, because we are not given the distribution from Oracle, so we just do some sampling from historical data, or we do some querying, like in some market research, things like that, to get some information. And so people are studying like the sample complexity or query complexity in optimal mechanism design. There are many interesting work here. Also, maybe finally we get some distribution. So, but the distribution is maybe have some errors, which is kind of some distance from the true distribution. So in this way, can we really can we still design an auction which is kind of robust against the uncertainty in the distribution? There's many studies here, and here actually another issue is that the correlation. Because in all our previous discussion, we assume that the distribution for different buyers are independent, which is a kind of too strong assumption. Because as you usually in market, the valuation for different buyers are highly correlated. So there are two directions to attack the correlation. One is that if you really know the correlation, you may make use of the correlation to get more revenue actually. Because if there are correlations, you can kind of get more information from one bit for the information of others. So, but this is a kind of more optimistic way if you really know the distribution and even their correlation. But the other is called a correlation robust. So in that, this is the topic I would like to briefly discuss here. So in a correlation robust mechanism design, so we are given the margin distribution because we can learn that from some historical data. But actually, it's really difficult to learn the correlation, to learn the joint distribution because the size of the joint distribution is exponentially large than the margin distribution. So we can only design mechanism based on this margin distribution. But we know that they are possibly correlated. So the auction. The revenue is evaluated in the worst case over the uncertainty of possible joint distribution. So basically, we design the mechanism only based on the margin distribution, but we evaluate the mechanism by a joint distribution, which is a kind of worst case to our mechanism. So this model is first proposed by Carroll in a top economic journal, and he studies the multi-item and single buyer setting, and we actually extend that to a setting with budget. So here's a mathematical formula for the correlation robust. So we know the marginal distribution of the buyers, but we don't know the joint distribution. And once we design a mechanism, the revenue mechanism is evaluated with the worst case joint distribution. So this is a worst case joint distribution which consistent with the marginal. Here's the condition. So we require that the joint distribution is consistent with the marginal, but otherwise it's the worst case one. So this is so in this case, even given a mechanism, it's not easy to determine what is the worst case revenue, and but we want to design a mechanism which is maximize this quantity, which itself is also an optimization problem. So since I'm run out of time, I will skip that. So Carroll's result showing that for additive bias and the optimal correlation robust mechanism is selling the items separately. So just do the item pricing. This is a very interesting. Although the problem kind of become difficult, but showing that in this model, the optimal mechanism becomes simple. It's item pricing. As I said before, for the multi-item setting, if you do the independent setting, it's not the selling items separately is not necessarily optimal. It's actually it's sometimes it's better to do it like bundling or other more complicated mechanism. So this is the one I mentioned. So you want to design a mechanism maximum this quantity, but this quantity is a minimized over all possible joint distribution. So this is a max mean. It's quite complex. And this result is kind of intuitive, but it's very difficult to prove because in Carroll's paper, he construct this joint distribution as a random process, and it's quite complicated. And actually, we with Nick Graven, we actually proposed a dual perspective. So this is the ALP formulation for the minimal for the worst case revenue, and if we do the dual ALP for that, we introduce dual variable, and this minimization problem become a maximized problem. And the good part here is that in the dual ALP, the unknown joint distribution pi is not there. So in this in the prime ALP, there are exponentially many variables, and in the dual ALP, there are only polynomial many variables. And of course, there are exponentially many constraints, but that's easy to handle. And another thing is that it's become a maximal problem, and you can put these two maximal together, so it become a single ALP problem. Previously, it's a maximum problem. And for that, we can actually do the calculation, solve the ALP to get the optimal mechanism. And our result is showing that even the additive buyer has a planned budget, the optimal correlation robust mechanism is still selling items separately. And from the technical perspective, we're using this ALP solution, we avoid the difficulty of construct the worst case distribution, which is all exponential size, and we prove a stronger result. So we also initiated the study of single item auction, because previous result is about single buyer and multiple item, so which is a simple setting. And here we initiate a study about the single item multiple buyer setting, which is the main setting. And in this correlation robust framework, and here we using some example showing that it's not really possible to give a simple formula for the optimal mechanism, but we prove that the sequential posted-pricing is approximately optimal with a constant approximation ratio. So, but here many problem remains open. To sum up, so we mainly studied the Beijing revenue maximization problem. We started that from two perspectives: the simplicity and the robustness. We said simplicity is simple auctions might be suboptimal, but they have other advantage, and we characterize the revenue gap, the worst case revenue gap between a simple auction with a more complicated one. And we also study the robustness. We have this framework of correlation robust. And I think this is a very interesting area to study, and there are many open questions. And I would encourage the students to look at that. Okay, that's all. Thank you.
Thank you, Pinyan, for your wonderful talk. So I have a few questions from the audience. So one is, what do you think is the best way to measure the simplicity of a mechanism, especially in the single item setting? Is it possible to formally capture the idea of a simple mechanism?
Okay. Yeah, as I said, I think for the non mechanism, this anonymous pricing is the simplest one. The seller simply set a price, and for the buyer, it's just take it or leave. I think this is simple, and this is a kind of a hierarchical structure in terms of simplicity. So as I said, this one, these two. Are simple than these two in the sense that there's no prime discrimination, and these two are simple in the sense that they are pricing scheme rather than auction. So here we mainly formulate the simplicity using these two perspectives. One is it's a pricing or it's an auction. Another is that it's anonymous or it's not. So it's like a discrimination is allowed or not allowed. I think these are the main angles, but of course there are possible other perspective to study, which is simple and which is not simple.
Yeah, interesting. Another question is it possible to extend this result to multi-dimensional auction setting? You did, right?
Yeah, as I mentioned, for multi-dimensional, it's much more complicated because even the optimal auction is not known. So there's some study, for the simple versus auction, like it's proved that selling separately or selling as a bond, the best of these two auctions is a constantly approximation of the optimal one. So I think there's some study, but it's like the gap, the revenue gap is it's not really. I think it's far from getting an optimal gap, but there's some studies showing that it's constant bound or things like that.
Actually, I have a question following up on the first question there. You put like anonymous pricing under the button, so you think it's the simplest one. But my question is on the other direction. It's for anonymous pricing. You mean it's you don't remember this. So for each person, the pricing is
uniform. Same.
Yeah, it's uniform. You don't do you mean you don't remember its data, or you remember data as the data from the whole group?
Yeah, we remember the data from the group. Yeah, here here anonymous pricing we mean that we are able to set the optimal price for that. So which requires the distribution information from every single agent. So yeah, that's actually the study of the second part of the robustness. If you only have a partial information of the data of the distribution, can you really set a price which is still close to the optimal? That's like the sample capacity or other. That's the study of the second part of the talk. Yeah. In the first part, we assume that the distribution is given completely.
Yeah. Okay. Yeah. Thank you. So thank you very much to give the wonderful speech, and we can move to the next stage at this point. Thank you very much. Yeah.
Thank you.